So I already sent.
This call is now being recorded.
I already sent the worked out solution in the group. So I'll be presenting. Yeah, basically. Okay. So I'm doing Legendre. Yeah. So the first thing I want you guys to remember is that Rodriguez formula. It's like it is the one you use when it is the formula you use when you want to generate your Legendre polynomials. So for example, the way in Legendre we normally have P naught, P1, P2, P3 of X. It is Rodriguez formula you use. So you have to remember this formula because it will help you to generate your polynomials. So yeah, so you have that. So remember this formula. So at n is equals to 1, is equals to 0, you'll come and substitute here so that you get P naught. So I'll come and do n is 0, 2 raised to power 0, d raised to power 0, dx raised to power 0, and also here raised to power 0. And anything raised to power 0 is 1, so I have 1 here for P naught. Oh, the question was saying, I hope you guys know what the question was saying. It said you generate using Rodriguez formula, you generate the Legendre polynomials for P naught, P1, P2, and P3. So that is what the question said. So again, at n is equals to 1, you'll just come and substitute in this formula. So you'll find 1 factorial, 2 raised to power 1, dn raised to power 1, dx raised to power 1, and this raised to power 1. So after you do that, you know 1 factorial is 1 times 2 is 2. If I differentiate here, I have 2x. So I'll have these two cancelling. So I have P1 of x is x. So that is normally how we find that. Now to get n is equals to 2, now for P2 of x, this should be P2 of x, sorry. You have 1 over n factorial, so 2 factorial times 2 raised to power n is 2, so 2 raised to power 2. And then you have d raised to power n, so d raised to power 2 dx squared, and then again this whole time squared. So yeah, if I do 2 raised to power 2, 4 times 2 factorial is 8. And then you do, because this is doing derivative twice. So first you'll expand this expression. You'll have x raised to power 4 minus 2x squared plus 1. And then you do the first derivative for you to get 4x cubed minus 4x. And then you'll do the second derivative. So you'll have like 4 times 3 is 12x squared minus 4. So that is where I ended up with this. So yeah. And then here I factored out 4 from here. So if I tower 4, I have 3x squared minus 1. So from there, I think this is pretty understandable. Half P2 of x is a half, because this is 4, 1, 4, 2, 3x squared minus 1. And then you do the same thing for 3. So this was n is equals to 3. So again, where there is n, you substitute with 3. So we had n factorial is 3 factorial times 2 raised to power 3. Then now here it's n is 3 again, and then it's 3. So the first thing you'll do, you'll expand this term. You can say x squared minus 1 cubed is equals to x squared minus 1 times x squared minus 1 squared. So that is basically what we do. What I did the square, and then I multiplied by the term again to get the cube. So yeah, this was basically just normal expansion, and then I put it back in the equation. Now remember, here you're going to differentiate 3 times because it's raised to power 3. So I did the first differentiation. Sasa hapa itabaki squared. Hapa ibaki nini? So I did the first differentiation. Nikapata ni 6x raised to power 5 minus 12x raised to power 3 and then 6x. I did the second differentiation. Nikapata nikapata 30 raised to power 4, x raised to power 4 minus 34x squared plus 6. And then I did the third differentiation. So 4 times 30 is 120, x cubed. Then 72x. Yeah, here is just normal. Yeah, factorial of 3 is 6 times 8 is 48. So that is what was going on here. Okay. So yeah, with that you've already generated your Legendre polynomial system.
Question, Celeste.
Yeah.
What's happening when you're looking at an n equals 1?
N equals 1.
Yeah, and notice the answer seems to come to x. Yeah.
N equals 1. What do you mean?
Yeah, you're right there. Like p sub 1. P sub 1 of x.
Sub 1. Okay. Oh yeah. Here.
So why is it that when you're differentiating the operator is not working on x squared minus 1, all that put in bracket raised to the power of 2?
Raised to power 2. Okay, so this is where. Sorry, come again. You're saying?
You notice for the other ones we're doing raised to the power of 2. Your x to the 2 minus 1, then all that.
Yeah. Okay. Yeah, I did that here. Only I differentiated
Where?
here because this. If I differentiate this term, I get 2x.
No. But why isn't it? Why doesn't in the brackets? Why isn't that whole term in the bracket raised to the power of 2 like the other terms? Like it's written in Rodriguez formula.
No, Rodriguez is actually to the power of n.
To the power of n.
Yeah.
Good lord. Kwani nimekuwa explaining this whole afternoon. Go back. Even
Go back.
oh yeah. Oh, so that's why. Okay, makes complete sense. Thank you.
Okay.
That's a jump there.
Any questions until there? I hope you've understood. So, by the way, if you guys remember this part, kwenye notes zilikuwa, it had some really not confusing, but some really, let me show you here. Yeah, there's this part we were being told to get sijui Pn of x, yeah, or this. There was a question he gave us and said generate Legendre polynomials up to degree 10. So hizi p naught, p1 of x, p2 of x, that is how we were generating them. You're actually supposed to use Rodriguez formula. So Rodriguez formula is used to generate Legendre polynomials. Even when you're revising, I think for Legendre you should start from Rodriguez formula. It's the basis for what you're going to use to generate your Legendre polynomials. So when you know this formula, you don't even have to stress about cramming what P2 and P3 is and so forth. So let me do the next one. So we were asked, use the orthogonality property of Legendre to evaluate the integral. Okay, we were given an equation. We were given this equation. So this was the integral we were supposed to evaluate. So for Legendre, if you want to evaluate for orthogonality, there is always this statement you're given. So you have two polynomials. One is subscript n, the other one is subscript m, and they're integrated in the interval -1 to 1. So the result, okay, if you get a 0, if this subscript m is not equal to n, so for example, if I have p0 and p1, or p1 and p2, or p1 and p7, it means subscript m is not equal to n, so inamaanisha hiyo term itaenda to 0. But if n here is equals to m, so if the product is p0 and p0, or p7 and p7, or p2 and p2, then we will evaluate. Okay, this is how the solution will get. We'll have 2 over 2n plus 1. So let's do it in a question so that you understand. So p2, so this is actually the function we're dealing with. This is the actual question. We want to evaluate whether it has orthogonality. So the first thing you have to remember, you have to express your whole function in terms of Legendre polynomials. So uta express in terms of p1 or p0, p1, p2, p3, depending on what you have in your equation. So kama for example hapa 3 is a constant, but I can't represent it as 3 because it has to be in terms of a Legendre polynomial. So 3 is like 3 times 1. Sindio? So 3 times 1, let me just get a pen. So I'm saying for, what is this? Okay. So for 3, it's a constant. I can't express it like this when I'm doing orthogonality because all my terms have to be in Legendre polynomials. So this is the same as saying 3 times 1. And we know p0 of x ni inatupea 1. So this 3 itakuwa 3 p0 of x because hii 1 tumereplace na hiyo p0 of x. We have 5x here. So here 5x, we know x tunajua p1 of x inanipea x. So this term I can say it is the same as 5 p1 of x. So basically I know the Legendre polynomial yenye itanipea x ni hii. So I'll replace it here. And then yeah. So again here tutakuwa na 3 p0 of x. And then there is here. So here we want to replace this x squared. If you remember from our derivation, tumepata p2 of x is 1 over 2, 3 x squared minus 1. So I'll make x squared the subject here, and then I replace here. Because it's like I'll be expressing x squared in terms of p, and p is a Legendre polynomial. So this is just now arithmetic. I'll make this one the subject. So nitaleta hii huku ikue plus, and then I divide by 3 everywhere. But now you realize this is 1 over 3. Again, this is not a Legendre polynomial here. So 1 najua ni p0 of x. So nitakuja niseme p0 of x over 3. Don't use 1 over 3. I think this is a mistake I made in the cat naili. It really messed me up. So make sure you don't leave a constant there. Everything must be in terms of p, a polynomial. So this is your term for x squared, na ndio utakuja uingisha hapa. So itakuwa 4 times this whole term. X cubed again, we saw the third polynomial ndiko na x cubed. So you'll make it the subject. Yeah. So remember from deriving from Rodrigues, we were able to get the third Legendre polynomial. And then we'll make x cubed the subject. So when you make x cubed the subject, we will end up with this term. So in our equation, penye kuna x cubed, utasubstitute na hiyo. So hapa ndio utaweka hiyo hii equation yote ya x cubed. Anybody has any questions still there? Okay. Sawa. So and then now I'll come and substitute. So penye kulikuwa na so in this equation I'll substitute. So of course 3 itakuwa 3 p naught of x, 5x itakuwa 5 p1 of x, and then hapa tena 3 itakuwa 3 p naught of x, and then okay, niliweka ya x cubed kwanza, so this time ya x cubed nilingisha hapa, and then I have 4x squared, so 4 and then times the term 4x squared. So from here it's just arithmetic, because after substituting you'll expand. Utafanya the way we normally expand in math, and then you put your like terms together. So basically. So when I expand, I'll end up with these expressions. So this is where you're going to use this thing for orthogonality we were saying. Okay, the way we were saying that Pn of x, then Pm of x. And then we said if we evaluate from -1 to 1, if m is not equal to n, so if this term is not equal to this term, it's 0. The whole integral will go to 0. But if m is equals to n, itakuwa 2 over 2n plus 1. So let's apply it here. Ukiangalia hapa tuko na p naught na p naught. So hapa ni n yetu ni 0 na m yetu ni 0. So they are the same. So which means this term itakuwa 2 over 2n, n is 0. Okay? So 2 over 2n plus 1 times 13. So I'll have 13 into 2 over 2, n is 0. N is 0 because hapa tuko na p naught. So that's why. So hapo ndio nilikuja nikaandika hii expression. I think you'll get 26. If you go to the next one, if you check hapa, n yetu ni 0, hapa ni p1, so m yetu ni 1. 0 is not equal to n1. So this whole term will go to 0 because m is not equal to n. Hapa tena tuko na subscript ya 0 hapa na 2. They are not equal, so it will go to 0. So this whole term will go to 0. Tena hapa tuko na 0 na 3. Again, they are not the same, it will go to 0. Hapa tuko na 1 na 0. They are not the same, it will go to 0. Hapa tuko na p1 na p1. They are the same. So we'll have 2 over 2. Our n is 1. Term. So 1 plus 1. And then times 3. Of course, this whole thing times 3. So I'll have 6 over 3. Should be 2. Yeah. So this is what I've done here. That is where this is coming from. Hapa, they're not the same. Itaenda 0. Hapa it's a 1 and a 3. They're not the same. Itaenda 0. So in the end, the only terms that will not go to 0 is this one, na tumeweka hapa, na this one, tumeweka hapa. So you'll find it's 28. Any questions still there? Any queries? Rejand? So I think this question is free marks. If you're able to do this question, I'd advise you to do it. You just have to remember the Rodrigues formula. And that's it, because now you can generate your Legendre polynomials, and if you're coming to evaluate, if you've already derived, then it's easy for you to know what's going on. So if there are no questions, I'll let the next person take over.
Thanks, Celeste. Next is meant to be Madiba.
Hello. Hello.
I can hear you. Yeah, I can hear you.
Okay. Can you see my screen? Hello?
I can see it.
All right. So I shall be doing question number 3 for the Fourier series. And yeah, okay, we shall start. I'll start at part B. I'll explain later on why, if that's okay. So let's start. First part says that we sketch a graph of f of x for the interval -3 to -3 pi to 3 pi. So that's, yeah. So if this is a function we are given, we shall look at the limits. From -pi to 0, the function goes to 0. So from -pi to 0, the function goes to 0, which is here. And then from 0 to pi, the function goes to x, which is pi. So this is here. And then goes on like that. So that's pretty much it. So you do that from -3 pi to 3 pi, and you have your graph. Okay. I shall go to next question, part 3, which states, part 2. Obtain the Fourier series of function and hence use to use in the following series. Hence use in the following series basically. So when obtaining the Fourier series, the first formula on your screen right now, this one, is the general formula for the Fourier series, where we have 3 constants, a0, an, and bn, ranging from n, 1, 2, 3 onwards. So to obtain a0, we do 1 over pi integral of the function. This is just here for representation purposes. It's not supposed to be there. An, same, which is 1 over pi fx cos nx dx, for representation purposes, are the limits. And then bn, which is 1 over pi fx sine nx dx, same thing. All right, so we shall start the question. Right. So the first thing we're supposed to do is find the constants, and we start with a0. And we know our formula is 1 over pi, and then for the limits, which are -pi to pi, as given from the question over here. Yes, -pi to pi over here. And then you can also recognize them from the function itself, this being, this and here. Right. So fx dx, which is equals to 1 over pi. Because we have to, okay, from the question, since we have to, they say steps, I guess. This first part, which is from 0 to -pi and 0 to pi, which have different values, which result in different values for fx. We come to the question now. We break down our function fx into 2 parts, which is this is the first part and this is the second part. From -pi to 0, fx dx plus, and then 1 over pi from 0 to pi fx dx. And then we come and replace our values from the question, which are 0 and x. For negative pi to 0, it's 0, and 0 to pi, x. Come over here. So, where are we? Oh, here we are. So we come and replace the values 0 and x for negative pi to 0 and 0 to pi, and then integrate. So from the first part, we get 1 over pi, x squared over 2 pi, and then 0, which is equals to, sorry, what am I saying? Sorry, this goes to 0. First of all, this goes to 0, and then we integrate this, which we get this. It gives us this, and then at the end results in pi over 2. And that is the value of an. Sorry, a naught. So this is a naught. We go to an. An, the formula is 1 over pi from negative pi to pi fx cos nx dx. We do the same thing. We split it into 2 components because of the 2 steps in the function we're provided with. 1 over pi, and then negative pi to 0 fx cos nx dx, plus 1 over pi 0 to pi fx cos nx dx. So we start 1 over pi. If we look at this already, when we replace the fx with 0, this already goes to 0. So that goes. So we come to this one, and this is what we are going to integrate. Right. From integration by parts, you shall get 1 over pi x sine xn over n pi to 0, and then the other integral will be 0 to pi sine nx n dx. Integrate this, you get an being 1 over pi sine, and then all this minus 0, 1 over n minus cos nx pi to 0. Right. So first thing is when we replace this equation here, we shall get, when you replace this n, yes, we'll get 0. So not n. Or sine, when we replace n with 1 or any value, sine pi will go to 0. So this equation all goes to 0. That's why it's not there. So 1 over pi into brackets 0 plus, which is our second equation, because when we replace n with any value 1, 2, 3, it won't go to 0, such as sine. So we'll have 1 over n squared cos nx 0 to pi, which we calculate to get 1 over pi n squared minus, So, I see what happens here. This goes to 1, and then when you come here, there's a trigonometric formula that says, I don't know if you can see it here, cos n pi is equals to negative 1n. So when we replace this cos n pi in the equation, you get 1 over pi n squared into brackets negative 1n minus 1. So this is what we get here at the end. And then we come and do this. So since we have n being a range of values from 1 to 1 onwards, so we'll just take the first two, 1 and 2. So when n is odd, for example, when n is 1, negative 1 remains negative 1. So we have negative 1 minus negative 1, which is negative 2. That's why you have negative 2 over pi n squared for when n is odd. But then when n is even, we get that this becomes 1. 1 minus 1 is 0. Whatever this becomes 0. This is why we have this part here. And that is the first section of the calculation. We shall go to the second part. Right, for Bn, same thing. The formula 1 over pi fx sine x dx is equals to 1 over pi. We break it into 2 parts. The first part and the second part, ranging from negative pi to 0, fx sine nx dx. And then for the second part, from 0 to pi, fx sine nx dx. Right, we substitute the values. 0, the first value which is 0 and the other one is x. Looking at this, we see this goes to 0, so we don't have that part, and then we remain with this. 1 over pi, 0 to pi, we integrate, we get this equation here. Again, it's integration by parts. We get 1 over pi, all this, negative cos nx minus the second integral, 0 to pi. We integrate this again, we get this result. Sorry. We get this result. Right, so we have this equation, and again, we can recognize that. Next. Sorry, give me a minute. Yeah, we can recognize that when we have any value of, when you have any value of n here, this all goes to 0. So that's why we don't have this part. And then from the formula that I showed you before for cos n pi, which gives us this, we end up with 1 over this. Okay, sorry, this cancels out with this, and then we remain with 1 over n, and then the cos n pi is replaced with 1, negative 1 raised to n. And then we do the same thing. If n is an odd value, it remains with negative 1. Sorry, yeah, it remains with negative 1. And then we have 1 over n, because this rule multiply, giving us 1 over n. If it's even, this becomes 1, we get negative 1. So we have our value for an, a0, and bn. To simplify your work, you can just create a table or whatever suits you most. We come to an here. We have different values of n ranging from 1 to 5. So from the equations we formed at the end, we got this one and this one over here. Sorry. This one and this one. This is how we generate this table over here. I shall use the second one because it's easier to see. Okay, so we come here. When n is 1, which is odd over here, 1 over 1, we get 1. When n is 2, which is even, we get 1 over 2, negative a half, and so forth and so forth. It can also be seen for this other part over here when n is even, we get 0, which is here, even numbers 0, 0. And then when n is odd, we have negative 2 pi n squared. So come over here. So when n is odd, we have negative 2 pi. Now n will be replaced by 1, you get negative 2 over pi. For 3, it becomes 2 over pi, 1 over 3 squared. And then for 4 is 0 onwards. Right. So with what we are having the constant and the formula for the Fourier series, which was on the first page, having all our constants and the formula itself, we can come and generate our Fourier series. So we have pi over 4 minus 2 pi, which is for the, sorry, let me just come here, a0 over 2. And we have our a0 as pi over 2. So we get pi over 4 as the first value, minus, so for this section, for this part for an, we have this. Yes. Yeah, here we are. We have these values for -2, which is constant in all of them, so we can factor it out. So -2 cos x, and then for 3 we have 1/3 cos 3x. For when n is 4, we have 0. For when n is 5, we have this, and onwards. And then plus for the sign bit, we have for when n is 1, we have sin x. For when n is 2, we have 1/2 sin 2x. And then for when n is 3, we have 1/3 sin 3x, which is, yeah, from all this basically. So, yeah. Now we move on to the other part, which is, wait, no. Okay, wait, so before I move on, this is our Fourier series solution. Now, let me get back to number 1. Okay, when I was doing the question, when it came to number 1, I wasn't sure how to do it, but since I could recognize from number 2, I was going to form a Fourier series in the calculation itself. I didn't do this first and just came to number 2, did part B, all of it, and then after getting my Fourier series, which is this, I just replaced, sorry, I replaced it to number 1 here. So that's how I came up with number 1. If there's another solution, I would like to know. Please present it. And I guess Nigel shall continue with the other section.
Dibs.
Yeah.
For that particular question,
Yeah.
I think what they were asking you is for the Fourier formula.
Oh, the formula itself.
Yeah, just the formula. So you go to the general. You see that general
this
yes,
one.
right there. That's it.
Oh, right. So yeah, for number 1, according to Joseph, we just write the general formula. Right. So Nigel shall continue.
So thank you, Diba.
Right.
Let me present my screen. It's really raining this side, so kama unanisikia vizuri, just type yes.
Tunakusikia.
Okay, cool. Okay, you can see my screen. Let me move on to where I know the question. The function fx, hence use a series to show that 5/4 is equals to 1 minus 1/3 plus 1/5 minus 1/7 to show this Fourier series that we obtain are equal to these two of them. So we shall start this first one to know before delving into that question. Kuna formula zenye Biba ametumia, so huku ndo penye zinatoka. Let's start. This is our general sin x function, like this, with a period of 2 pi. So in Fourier series, it's supposed to be, it's not being shown up. Sorry. This title, I wanted you guys to see this title. It's supposed to be useful trigonometric results or something like that, but kwa document yenyewe mnaweza iona. So results for a sine function, a sin x function, where n is equals to 0, 1, 2, 3 are true for the same as 0, negative 1, negative 2, negative 3 from this other side and this other side. And when we take a sine n pi, we get a 0. So sum to cos x, this is our cos x graph with a period of 2 pi. So the same thing for sine here. Now it will give a different answer for cos. So cos n pi is equals to negative 1 power n from this graph. Alafu another useful information ni for cos x, whereby x is pi over 2, it will give such an answer, such that it will be for cos n pi over 2, when x is pi over 2, it will give a 0 when n is odd, because cosine functions zinapeana values when the values zenyewe ni even. For an odd nini itapeana 0, and it will be a 1 when n is 0, 4, 8, 12. So there's a difference of 4 in each of the numbers. And it will be negative 1 when n is equals to 2, 6, 10, 14. There's a difference of 4 in each of the numbers, but now for negative 1, it starts from 2. So for the same thing applies to the sine function. So when we assume x is pi over 2, or sine n pi over 2, there's a sine graph function. So itapatiana a 0 when n is even. I hope you guys can see this. It will be even because sine functions in our odd function itapatiana value 1 and negative 1 when it is odd, but itakuwa 0 when it is even. So for 1 itapatiana when n is equals to 1, 5, 9, there's a difference of 4 in between. So the next value itakuwa 13, then 17, then continuing. Itapeana it's 7, 11, there's a difference of 4 in the last 4, itakuwa 15, the next one itakuwa 19, itapeana negative 1. This is supposed to be a negative. So with all that information, we may summarize and it will, when n is an even function, it will give 1. When n is an odd function, it will give negative 1. So something for when x is pi over 2 ndio hii, just summarized it. I highly recommend that kama unafanya exam ya maths na unachukua swali ya Fourier series, kwa kana hujashika hizi nini, just take a sticky note alafu uzieke kwa ukuta, because you'll really need them when we apply to when you're doing such a question. So back to our question. For when we're supposed to show this, hence use the series to 5 minus that. So this is just what I did. This is what I did. Hope it's clear. So this is a function. We're supposed to compare it with the function that we got. And the function that we got, that Madiba got, was this. So we're supposed to compare the two functions. So when you compare the we'll go back to where umesema tuweke sticky notes, niandike sorry. Oh, okay. Easy. What I started explaining here, Mike, it's just information in itatusaidia ku analyze that question. So in a Fourier question, zenye nimeona zimesetiwa kwa exam, they have that part, and this is generally needed. It's just a summary of this over here. Utaona mbele where it is used, but this is important. Utapitia tu mbele, then you'll see how important it is. Kwa wenye wameshika, well and good for you guys. Mtapita mtihani. Aya, tuendelee. Where was I? I was comparing the two functions. So this and this. When we notice from this function, let's consider now this right-hand side, achana na hii side kwanza. It has 1 minus 1 over 3 plus 1 over 5 minus 1 over 7. So tukiangalia hapa gani ndio inakaa kuwa equal to it ni hii ya sine, because hii iko na every value of cos iko na a square in its denominator. So we are supposed to now this value of cos the such we have a sine x minus 1 over 2 sine 2x plus 1 over 3 sine 3x. Yeah, but here and we need to make the even values of sine to disappear. And how do we do that? Tunarudi hapa juu. Which one inaweza tusaidia ku make the cos disappear na even values of sine could disappear from all of this? I found it was we use x as 0, because when you put sine x over here to be it was not 0, sorry, it was not 0, it was pi over 2, x as pi over 2. I was just comparing all three of them. So when we input x here as pi over 2, I replaced the x values over here with pi over 2 like this. But from the facts that we've known huko juu, cos pi over 2 for odd values will give 0, and all our numbers of cosine functions, the n now, they are all even. So from here, let me zoom in. From here, if it is odd, it becomes a 0. So this whole thing becomes a 0. So tunabaki na pi over 4 plus the sine functions now. Alafu from sine functions, sine 2 pi over 2, when for sine functions, sine n pi over 2, it becomes a 0 when it is even. So the even values it will disappear. So hii itakuwa 0, kama kungekuwa na 1 over 4 sine 4 pi over 2 ingekuwa 0. So tunabaki na sine pi over 2 plus 1 over 3 sine 3 pi over 2 plus 1 over 5 sine 5 pi over 2, continuing. So it will boil down to this. It all boils down to this. And when we see from this is supposed to be fx is equals to this, is equals to that. So, and remember we found our x to be pi over 2. So our x from pi over 2 equation yetu, we go back to our graph yenye tulipata from the beginning. We say when x is pi over 2, so hapa, what will be our value of y? Value of y yetu pia itakuwa pi over 2. So our f of x also will be pi over 2. So niliweka hii fx as pi over 2 equals to pi over 4 plus 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus blah blah into this. So function yetu reduce down to that, to this. So simplification gives this as the answer, and that is what they were asking. So yeah, sorry, that is this. So kuna mtu akona swali ama tuendelee kwa ya pili? Okay, tuendelee. Pi squared over 8 is equals to 1 plus this plus this. So the same process, we compare the two functions. So this is our function now. Remember 1 plus 1 over 3 squared plus. So we look kwa hii function yetu yenye tulipata hapa juu here. Which one is similar, and or which one will when we solve it will be more equal to this. So tukiangalia yenye iko na squareds ni cos, so our cosine will definitely remain, but our sine, they will have to disappear. Now, what value can make our sine disappear and make our cos remain? Make our cos remain, yeah. I found that value to be 0, because from hapa because 0 is 1 and sine 0 is 0. So all the sine functions itakuwa 0, all the cos functions itageuka. Cos 0 of that particular number of cosine function itakuwa 1. So I replaced everything hapa, this function yenye tulipata, yenye Wadiba alipata, with cosine. They turn into 1, and the sine functions, they all turn to 0. So what I got was this. Remember our fx. This function yenye nilipata on the right, tukirudi kwa graph yetu kabla tulifanya tu kwa ya kwanza, what fx on the x-axis, there's supposed to be an x. It looks like a k though. Graph yetu iko wapi? Here. A 0 of x will also give a 0 of y. So fx will also be 0. So 0 is equal to this side. We take 2 over pi to this other side, and we substitute it. We multiply pi over 4, multiply by pi over 2. It becomes pi squared over 8. Up and a simplification to simple stuff. And then boils down to this as your answer. Boil down now. Okay. Boil down now. Boiling inaendanga up generally. Yeah. But that's the answer. Kama kuna mtu akona swali, I raise, because mimi nishamaliza swali yangu. Alafu just a quick note. Just a quick note. Kuna PDF yenye alituma ya Fourier series. Amelift hiyo swali directly from your PDF. It's question 2 actually. It's question 2, and I've noticed kwa number 1 yenye I think Sean anafanya, there's a question on Fourier series. I may lift from upper. This PDF has like 7 examples, na each examples zikona answer each huku chini. It's count as a bit easy examples, then kesho kuto utakuwa very okay. That's it for me.
Nigel, could you be so kind to send the PDF over to the group?
Yep. Wacha naituma tu sahi.
Thanks.
Okay, I think now it's my turn. Can you see my screen?
Yeah, you can say it.
Yes, we can.
Yeah, we can see.
I was doing question 1. Here. Consider the power series below this one. Then you determine the interval and radius of this series. So first of all, you just need to know this formula, that L equals to the limit of n plus 1 over n. And this is magnitude. This is very, this will help a lot, especially if like some negative signs come about. Then now you need to know that also that radius is 1 over L. So here, negative r plus x naught, then r plus x naught will give the interval. So this is the general format of a power series function, but this is what we were given. So you have to take note that inside the brackets, the x has a coefficient of 1, whereas we have 4 over here. So you'll need to factorize that out. So remove that. I got 4 to the power of n because of this n over here. Factorized out, you get 4 to the power of n over coming out. This to become part of an, like this. So the next value of n plus 1 would be 4 over 4 to the power of n plus 1 minus 3 minus 3 to the power of 3 plus n. Then this n squared you'll square n plus 1. It won't be n squared plus 1, but n plus 1 in brackets squared. So you'll get n squared plus 2n. Then the plus 1, I just added straight away to this one. So you get this. So you then divide n plus 1 over an, which is this whole mess over here. But if you just bring all these like terms together, you'll see that the powers can straight away cancel out. So like this 4 to the power of n plus 1 over 4 to the power of n, you straight away get it's equal to 4. Then over here, this minus 3 base, you can just do 2 plus n minus 3 minus n. That will straight away deal with that. Then this part, you can just leave whenever you have an n as a base, you can just be leaving it. You don't have to worry about it as of now. Just try to, first of all, get all these similar parts together and cancelling out the powers. Get here 4 times negative 3 to the power of negative 1. Then with this function, this fraction, can just divide the numerator and denominator by n squared. Get this. Then since we're getting n as it approaches infinity, 1 over infinity equals 0. So get this. So you get straight away L equals to 4 over 3. The inverse of L will give us the radius. X naught here. You see X, we got the format of the formula is X minus X naught. Because straight away just get 3. So you get this as the interval. So now for B, briefly explain the following and give an example of each case. So a function which is odd in the interval of negative pi to pi. So this one is straightforward. A function is odd when negative fx equals to f negative x. So I then use the function sine. It straight away you can prove and shows sine is an odd function. Then for part 2, convergence of a power series, this one. A power series is all these definitions came from the notes, so you don't have to worry about Googling them. So power series is said to converge if the sum of that power series is finite. Then you can check if it converges using this formula. And if rho is less than 1, then the power series converges. So for my example, I just came up with some arbitrary values. This is straightforward. You can just say n is 1 over 4 to the power of n plus 1 will be like this. X naught, I chose it to be 0. Since it's my example, I can choose what I want. And I've chosen it to converge at x equals to 2. So rho is equal to, it's just straightforward, just substituting in the values. So you'll get that rho equals to 1/2, which is less than 1. Therefore, this power series converges at x equals to 2 when x not equals 0. So you've answered the question just like that. Part 3, a function which is analytic at the point x naught. You can just ignore this. We got this formal definition from Gicheru. It said a function fx is analytic at a point x equals to x naught if it can be represented by a power series in powers of x to x naught with a positive radius of convergence. Do I know what that means? No. But from the notes, we saw that for the note, which part was this? This part where when we are just showing the format of a general second order ODE, we said that in a function would be analytic at the point x naught if p1 over p2 and p naught over p2 are not equal to infinity. This is the first case. The second case, if it's equal to infinity, you can go straight to the second case, which is if x minus x naught times p1 over p2 or x minus x naught squared over p naught over p2 are not equal to infinity. So if both of these, if both of them get infinity, then the function is not analytic at that point. But if either of these get a fraction that's not equal to infinity, then you can say that function is analytic at that point of x naught. So for my example, I used the one from the exercise book, the one from our notes. The one you can just check for yourselves. Like, I haven't changed any part of it. I didn't see like any need to. Then for part 4, it's set of functions which is orthogonal in the interval a to b. So this is also from the notes. Like all these definitions, I got them from the notes and the examples as well. So it's more of straightforward like stuff. So are there any questions? Let me check. Nope. So determine the solution of the following equation, which is finite at x naught. So this is Bessel's differential equation. It's also from the notes. This question was taken straight from our notes. So first of all, you'll see that this part over here, it's meant to be x squared minus p squared. The coefficient of x squared is meant to be equal to 1, but now we have 16. So we need to try and reduce it up to 1. So at first we divided the whole equation by 4, which got this. Then we decided to let z equals to 2x. So that instead of having x as the variable throughout the equation, we'll change all of this to become one variable. So that's why we chose z to equal to 2x, so that this becomes z squared. And then now the problem is now that we've changed this part, we also have to change for the whole equation. So since now you've said z equals to 2x, we have to get this. This is the first derivative of yx, second derivative of yx. So now we have to get first derivative with y with z as the variable. This is why we use the chain rule over here. dy over dx equals to dy over dz times dz over dx. Over here, we chose z equals 2x, so dz over dx will straight away be equal to 2, which is what I'd written over here, 2. So dy over dx will equal 2 to 2 dy over dz. This is what we'll use to replace this first derivative of x. So now we have to get the second derivative, our new second derivative, which will just derive what we had over here. So d over dx of first dy over dx, which we got as 2 dy over dz. So I've just factorized out the 2. So now we're just doing the derivative with respect to x of dy over dz, which we got dz over dx equals to 2, because this one. So that will give us 2 over d over dz, which now we'll just bring this one back over here, which is what we've done over here. So you get 2 times 2 over this whole part. So you get it's equal to 4, the second derivative of y with respect to z. So now this part and this one is what we're going to substitute back into our equation over here. So that's what I did. So this 4 Second derivative, I substituted it back here. So 4 over z squared over 4. That z squared came from equation here. This x squared, remember we said z equals to 2x, so x squared will equal to z squared over 4. That's what we've done over here. So z squared over 4 times 4 second derivative of y. This x, this x, z equals to 2x, so x will equal to z over 2. So z over 2 times 2, the first derivative. Then remember we moved this 4x squared was equal to z squared. So that's what we did, z squared minus a quarter. And yeah. So now from this is our new equation. So this is our p value, p squared value, sorry. So p will be the square root, which is a half. Then now since p is an integer, we'll use this equation. And remember, since now our new variable is z, we won't write x inside, we have to write z. Then you can then put substitute back the 2x. So yeah, that is question C. Now for D was the same Fourier series as the question Fina, Madiba, and Nigel did. I got stuck at the integration part, but now that I've seen how they've done it, I'll try to do it again. Then I'll send that to the group together with my solutions for part A to C. So yeah, and then any questions? Okay, I'm done. I think next was meant to be Peter.
Okay, hello everyone. So I attempted question 4, which is what I'm going to take us through. Question 4 is about Laplace transforms. Yeah, so I'll first present my screen. Meanwhile, can you guys hear me?
Yes.
All right. Okay, so question 4. I hope you guys can see my screen. Someone please.
Yes, you can see the screen.
Question. Let f of s be equal to the Laplace transform of f of t. Denote the Laplace transform of f of t. Determine the first derivative of the Laplace transform and the second derivative of the Laplace transform, and hence deduce the expression for the nth derivative of Laplace transform. Right, so we'll do this first part and then we'll come back and do this second part later. Yeah, so let's see. So Laplace transforms. What exactly is a Laplace transform? So it's basically how to represent functions in a different domain. We are used to the time domain. So a Laplace transform transforms a function into another domain, commonly known as the S domain. So mathematically, the Laplace transform can be represented as this. So f of s is basically to transform a function into S domain. You get the integral of this e to the negative st, and then you multiply by the function. So this is the formula we are going to be using to get the Laplace transform of any function that we have, right? So this is how we can write it generally, that f of s which is the function in S domain, can be the Laplace transform of the function in time domain, right? So we are going to remember that this L here represents Laplace transforms, and this is its mathematical expression. Yes. So I guess with that, you can look at the first example. We have a function here, e to the at, and to get its Laplace transform, we're basically going to input this e to the at because it's our function into f of t over here. Yeah, so if you have the two, you're multiplying them, so they have the same base. We can put one base and do the thing with the indices. So then it becomes e to the negative into s minus a. Becomes s because we are adding this one, but we have introduced the bracket, so it becomes e to the negative s minus a. If you find its integral, it becomes negative because the power is a negative, 1 over s minus a, because whenever we are getting the integral of any exponential, we take its power and then we invert it and then we multiply it by the same thing. So that's basically what I was doing here. And then we integrate it between 0 and infinity. Yeah, so we have this term here remains, and then for anywhere we have t because you are integrating it with respect to t. So for the first infinity, it's going to be negative infinity, and then the second one is going to be raised to 0. Right, so this term here is going to boil down to 0, or boil up to make Nigel happy. So it's going to boil down to 0, because e to the negative infinity is basically dividing this whole term with negative infinity. And it's going to be a really big number. So if you divide whatever number with a really big number, infinitely big number, it's going to give us a 0. And then this second term here is going to be a 1. So it's going to be negative 1, right? So if you multiply this negative 1 by this negative outside, gives us a positive. So in S domain, this function here, our function e to the at, can be represented as 1 over s minus a in the S domain. Okay, let's look at another example again. This time we have a Laplace transform of 1. 1 is a general number we know. So to find its Laplace transform, we just plug it in the Laplace transform formula again. So this time around we have a 1. If we integrate this first part that has the exponential, it becomes a 1 over s. Again, any integral of an exponential is the inverse of the power multiplied by the same thing. It's indestructible. So we integrate it between 0 and infinity. So we remain with negative 1 over s into e to the negative infinity minus e to the 0. So e to the negative infinity is going to be like 1 over e to the infinity, which is going to be 0, because dividing a small number with a really big number, then this second part becomes a 1. So the negative from the brackets times the negative outside the brackets, you get a 1 over s. This here, you can confirm it from this first example. The Laplace transform of 1, if you want to make this a 1, it's only going to be a 1 when a is 0. So the Laplace transform of 1 here, when a is 0, is going to be 1 over s, because a is going to be 0 here. Yeah. So these two examples are just to show us that we can get a Laplace transform of any function whatsoever, provided we plug it in our Laplace transform formula. So then that's exactly what the first part of the question was asking, because we have we've been told we have f of s, and we want to find its Laplace transform. So we want to determine the Laplace transform of the first derivative of a function, and the Laplace transform of the second derivative of a function. So we'll just do the same thing again, but this time round with f prime and f double prime. So to denote the Laplace transform of f of t, this is its formula, f of t. So for f prime of t, we're going to plug our f of t this time round is f prime of t, right? So since we are integrating a product, we shall use integration by parts. So this is the formula for integration by parts. We let this be our u. So then our du is going to be negative s e to the negative st dt. And then we let our v be f prime of t. So this should have been a dv. Yeah, this should have been a dv. So we let dv be equal to f prime of t dt. So our v will be the integral of this. The integral of the first derivative of t is going to be f of t, right? So we just plug them in back into the formula we had for integration by parts. U becomes this, v becomes f of t. And then we integrate that between 0 and infinity, minus the integral of v, which is f of t, multiplied by du, which is negative s e to the s of t. I hope you're together up to there. So moving on, e to the negative st multiplied by that, we were taking it from 0 to infinity. So this first term from this one here, this first term, we are going to, it's going to be 0 if you look at it, because this e to the negative infinity is going to be the denominator. And since it's going to be a really big number, it's going to reduce this term here to 0. For this second part, this one, which is still the second part of this first one, but now from integrated from 0, we're going to have a 1 because of e to the 0 multiplied by f at 0. So this is here. And then for this one, we have an s outside, we have retained it, but for this term inside here, if you look at it keenly, it's the Laplace transform of f of t, right? Because we say the formula for Laplace transform is this e to the st to the negative st multiplied by a function. So now this here is going to be basically the Laplace transform of f of t. So we're going to replace it here. Now if we rearrange everything to make it look cleaner, we have SL of f of t minus f at 0. That becomes the first part of the question. We have determined the Laplace transform of the first derivative of any function. Now we want to determine the second part, which is the Laplace transform of the second derivative of any function. Right? So part B. Again, we're just going to plug it in the Laplace formula that we have. So L, the Laplace transform of this function here, is going to be e to the negative st multiplied by that function. Using integration by parts again, we substitute u for e to the negative st, and then we find du. We substitute for dv as well. We find v, and then we plug in everything in this integration by parts formula. So for the first part, we're going to have e to the negative infinity multiplied by the first derivative of the function at infinity. I hope that's clear. Minus e to the 0. Now we are integrating it at 0. E to the 0 multiplied by the first derivative of the function at 0, right? Plus, now we are moving on to this second part. This negative s here is a constant, so we can pull it out. When we pull it out, negative s times a negative, we get a positive. So it's positive s into e to the negative st multiplied by the first derivative of the function of t at dt. Again, just like we did it in the previous one, this last part here represents the Laplace transform of the function at the first derivative of the function of t, right? So this first part boils down to 0 because of this denominator that is really huge. This second part, we have a 1 because of the e to the 0. Any number to the 0 is a 1 multiplied by this. So we have a 0 minus f prime of 0, and then s, the Laplace transform of the first derivative of t. But from the first part, from this part here, we had figured how we can represent the first derivative of t. The Laplace transform of the first derivative of t, we can represent this. We can represent it as this thing over here, this solution. So we're just going to substitute that solution into this here, right? So that's why I said over here, but the Laplace transform of the first derivative of a function of t is equal to this, as we had found out earlier. So then we maintain our s, but for the Laplace transform of the first derivative of a function of t, we are going to replace it to substitute it with what we had found in the first question. So multiplying through, we get s squared, the Laplace transform of the first derivative of f of t, not first derivative. So s squared of the Laplace transform of f of t minus s at f is 0. Now this was replacing this first part of our solution. So we have to include this second part as well, which is f prime at 0. So yes, that gives us this second part. So this becomes the solution. This is the Laplace transform of the second derivative of any function, really. Whenever you want to get the equivalent in S domain of any function that is expressed in a derivative, in a second derivative, then this is what we use. Right? So now we have the Laplace transform, how to represent a function in first derivative as Laplace transform and second derivative as well. These are going to be two important formulas because you're going to be using them to solve the second part of the question. So have them in mind. Okay, so now we can look at the second part. Let's see what the question is saying. Write down the expressions for the Laplace transform of the first derivative of a function of t and the Laplace transform of this second derivative of a function of t, and hence solve the initial value problem. Right, so we have been given an initial value problem here, and we have been given the initial values here. So at y is equals to 0, at y at 0 is 1, and y at first derivative is 2. Okay. So these are basically the properties we had. We have figured out that the Laplace transform of the first derivative of any function of t is going to be expressed as this here in S domain. So the Laplace transform of a second derivative follows the same pattern, and the Laplace transform of a third derivative follows the same pattern. So that way we can even express a Laplace transform of nth derivative of any function, which I think was the last part of this question. I'll do that and send it. But it basically follows suit. So I'll just do the solution and then send it to the group. So now before we take on our question, I'd like to do an example here, build on from perhaps what we already know into what our question says. So you've been given a function at first derivative, a function of t. We've been told that it's equal to t, and we've been given an initial value of 2. So y at 0 is 2. So normally how we would solve this question is by taking the antiderivative of both sides. So if you take the antiderivative of the left side, we have a y of t, which is what we are looking for. And if you take the antiderivative of the right side, this becomes a half t squared plus c. So to get the constant, that's going to be, the constant is going to be equal to y when y is 0, because t is going to be 0. This part is going to boil up to 0. So y at 0 is going to give us a constant of 2. So then our function y of t is going to be expressed as a half t squared plus 2. So this is what we already know, how to find a function from a given derivative, whether first, second, by using antiderivatives. So now let's see how we can use Laplace transform just for the same function. Let's see how we can use Laplace transform to figure out its antiderivative. Right, so if we take the Laplace transform of both sides of the same function, we have y prime of t. If we take its Laplace transform, it's the same as taking the Laplace transform of the right side of the equation. So it's a Laplace transform of t. So we already know how to express the Laplace transform of a first derivative of any function. This is the formula we derived, right? So now we have this, and the Laplace transform of the right side, which is the Laplace transform of t, we can get this from the table of Laplace transforms. So this is t to the 1, right? So if we look at the table of Laplace transforms, let's see. Just a moment. So if we look at the table of Laplace transforms, this here at number 3 will give us the Laplace transform of t, because t here is going to be raised to the power 1. So it's going to be, this is the general formula. If you have a Laplace transform of any term raised to a power, then it's going to be n factorial over s n plus 1. That's the general formula. So where n is the power. So here t is raised to power 1, so it's going to be 1 factorial over s 1 plus 1, so s squared. So we maintain everything we have on the left hand side, except now for the initial value that we had been given, we replace it to be 2. Okay, so we have this minus 2 is equals to 1 over s squared. So this 2 crosses over, it becomes this thing here, 1 over s squared plus 2. And on the left hand side, we remain with s, the Laplace transform of y of t. So if we divide both sides by s, this will be 1 over s cubed. And then the second term will be 2 over s. So then y of t is going to be the inverse of the Laplace transform. Remember now this s has gone because we've divided both sides by s. So we're just having the Laplace transform of y of t. So to get y of t, we're going to get the inverse of Laplace transform on both sides of the equation again. So on the right hand side, the inverse of the Laplace transform of this plus this. And the Laplace transform is it's an integral. So we can use this property of an integral of dividing or separating the two separating the two fractions and taking the Laplace inverse of both of them independently. So y of t becomes the Laplace inverse of this plus the Laplace inverse of this. Now, going back to our table of Laplace transforms again, when you have 1 over s raised to any power, it gives you this in t domain, in time domain. So y of t is going to be t, where n here is 3. So t to the 3 minus 1 divided by 3 minus 1 factorial. Plus, these two can be pulled out, just like we do with any integral. Remember, the Laplace transform is just an integral. We saw that the formula of the Laplace transform is just an integral. So we can pull a constant outside, and then we'll take the Laplace, the inverse of 1 over s, right? So y of t becomes t squared over 2. 2 factorial is basically 2, and then plus 2. The Laplace inverse of 1 over s is a 1. So yeah, this becomes our answer. And we see that it's very comparable to what we got using the normal antiderivatives. So this is how we can use Laplace transforms to find a function from its derivatives. So Laplace transforms make it easier to solve initial value problems. Yes, this looks like it's long when we are doing a basic function, but when we are given a function in its third derivative or fourth derivative, a Laplace transform becomes very important, and it solves the problem easier than just finding the antiderivatives. So now we can move on to our question. This is what it looked like. We have been given initial values. Y at 0 is 1, y at y prime is 0, is 2, I mean. Y at y prime at 0 is 2. Yeah, so we can represent it this way, where d squared is the second derivative of y, minus 3, the first derivative of y, minus 10y is equals to 2, right? So if we find the Laplace transform of each of these terms, we take the Laplace transform of the second derivative, the Laplace transform of the first derivative, the Laplace transform of y, and we also have to take the Laplace transform of 2, which is on the right hand side. Right. So this is the formula for Laplace transform of that second derivative. We know that it has these 3 terms. This is what we had already derived. So s squared into y of s, where y of s is the Laplace transform of y. So s squared y of s minus s into this minus y prime at 0. And then the Laplace transform of the first derivative is this part here in square brackets. So we multiply all that by 3, and then minus, we said y of s is the Laplace transform of y. Now on the right hand side, to find the Laplace transform of 1, of 2, because we had a 2 on the right hand side, to find the Laplace transform of 2, we can't find that directly from the table because you don't have an inverse of 2 directly on the table. So we can multiply 2 by 1, which basically doesn't change the meaning, but enables us to have something we can find a Laplace inverse of from the table. So the Laplace inverse of 1 is 1 over s. So then our equivalent in s domain of this 2 here becomes 2 over s. So we factor out the Laplace transform of y, which now we are representing as y of s. And then we collect all the terms with y of s. Then the right hand side becomes 2 over s. This s here, oh sorry, we have this s here becomes a 1, just s, because y at 0 is 1 and y prime at 0 is 2. So we're going to replace the initial values and then cross them over to this other side. Yeah, let's see what was happening here. Oh, yeah. So we have 2 over s plus 2 minus 3, which is minus 1. So we are going to first make all these terms have a denominator of s, right? So that's going to make it 2 over s. This is going to be s squared over s, because you're basically multiplying every time by s over s. Then this third term is going to be negative 1 times s over s. So then everything becomes over s, and we can multiply this here. When it crosses over, it comes to the denominator, and we can multiply it by s. So now we have a Laplace transform, everything expressed in Laplace transform, the Laplace transform of a function y, and we have its equivalent. So now, once we get to this point, we want to take everything back to the time domain. But then we can't do that directly because we don't have all this junk here. We can't find it in the table of Laplace transforms. So we need to find a way of expressing it in a way that we can invert it to back to time domain. So we find the equivalence of this denominator, which is s plus 2s minus 5. We just separate the fractions multiplied by s. So y of s is equals to this, and that is equal to a over s plus b over s plus 2 plus c over s minus 5. We want to separate them this way because we are trying to find a way in which we can get the inverses from the Laplace table. So then if we multiply everything by the denominator here, we are going to remain with 2 plus s squared minus s. This one here will be as plus 2a, because you're multiplying it but by these two terms. S is going to cancel if you multiply by the denominator. So we do the same for b, we do the same for c. And then basically here we're just trying to put the s squared terms together and the s terms together, and the a terms, anything that doesn't have an s, we also put them together. So for this to be equal to this, because we are equating them, this first part has to be equal to the coefficient of s squared. So then we equate that to 1. The second part has to be equal to the coefficient of s, so negative 1. Where is it? Yeah, negative 1. And then this third part, negative 10a, will be equal to 2. So if you solve for a, b, and c, we find a is negative 1 over 5, b is this, c is that. So now representing our solution here in S domain, but as an exploded fractions, sum of fractions, we find this. Now it looks clean because we have things that we can find the inverses from the Laplace table. So the inverse y of t now, getting back to the time domain, the inverse of 1 over s is the Laplace inverse of 1 over s is basically a 1. So negative 1 over 5 plus, why is this a plus? Why is this a minus? Should have been a plus. So plus 4 over 7, the inverse of 1 over s plus 2 is e to the negative 2, plus the inverse of 1 over s minus 5 is e to the 5t. Yeah, and all their coefficients. So that becomes the answer of our solution. So this here Laplace transform has helped us to find the solution to this question here, which would have been really hard if we were just using antiderivatives. So this is how we can apply Laplace transform to work out an initial value problem that has perhaps a fourth or fifth derivative or third derivative. Right, so that was all that was in the exam question. I guess we have answered everything. But there was another question I came across. This was a question we did in our CAT. We wanted to find the inverse of this whole thing over here. But before we go on with this one, is there any question? That's why they call it infinity. Any questions? Can you guys still hear me?
Yeah, you can hear it.
Okay. Right. So let's get the inverse of this one. So first of all, to find the inverse of a Laplace transform, we just, since we have a complex fraction here, we just want to find a way we can make it simpler, right? So we want to basically explode it in a way that we can find its inverse on the Laplace table, or at least an inverse that we already know. So first you'll want to make it a perfect square, because you can't separate this into the product of two fractions, right? So I guess the easiest way to find how to express it in terms of a multiple of fractions ni to find the perfect square. So finding the perfect square, we want to find the perfect square, but we're not going to change the meaning of everything that's in the denominator. So s squared plus 2s. To find the perfect square, it's basically this b term, if you guys can remember, b over 2 is all squared. So b over 2 here is going to be 2 over 2 squared, will give us a 1. But since we've pulled a 1 from this 5, now we just add a 4, right? So the numerator remains the same, but now we can express this part here as a perfect square. That was the whole idea. So s plus 1 squared plus 4, right? So now if we take the Laplace inverse, the inverse of the Laplace transform of the left-hand side, we want to have the Laplace inverse of the right-hand side as well. But then, looking at what we already have, even if we separate the fractions into two parts, we still can't find this from the table of Laplace transforms. So we need to break it down even further. From here, this formula, but what is it called? Index shift. It's called an index shift formula. If you have a Laplace transform, a Laplace inverse of a function of s, which is basically, if you want to take a Laplace inverse, you can pull out an e to the alpha t, and then add the alpha to the function, right? It's called index shift. I'm pretty sure you guys have come across this already, just doing your own studies on Laplace transforms. But this index shift enables us, it will help us to just simplify this fraction even further. So we have an s plus 1 squared here, which is what is a little stubborn. So we want to make it an s squared. Once we have an s squared plus 4, then we are beginning to get closer to what we can find an inverse of. So to find how to make this s squared plus 4, we're going to have to subtract a 1 from here, right? So that it's s plus 1 minus 1, or s minus 1 plus 1. So to do that, since from this formula we know that if we pull out an e to the alpha t, we add an alpha to the s. Then if we pull out a negative, e to the negative t, then we can add a minus 1, because this is negative 1 here. So we can add a negative 1 to our s. So basically we multiply all the s's we have with, we replace all our s's here, not multiply. We replace all the s's here with s minus 1, right? So s minus 1 plus 1 is basically going to be s squared. S plus 1 here minus 1 is going to be s squared. So we introduce an e to the negative t, but it cleans up our fractions. So e to the negative t, the Laplace inverse of all of this again. The s here, 4s here, because you're replacing all the s's with s minus 1. It's going to be 4 into s minus 1. We're almost there. So 4 here is a constant. Laplace it's an integral. So we can pull out the 4 because it's a constant. So we have a 4 e to the negative t, the Laplace inverse of everything that is left. So this first part again, this first part after pulling out the 4 from the brackets, this s minus 1 can further be split so that we have an s over s squared plus 4 minus 1 over s squared plus 4, and then plus this e, because we are retaining the e that we are multiplying with here. This e still remains for this 2. It's just expanding this. So you want to be careful because there's a lot of details here. So e to the negative t, the inverse of this whole term. Now we've gotten really close because the terms we have start to look closer to what we can find inverses of. So this first term, if you find the inverse of this first term here, unapata ni what? Shoot. Sorry. So if you find the inverse of the first term here, you find it's 4 to the e negative t. This here, its inverse is cos 2t minus, in some tables, you will find how to find this inverse directly. But since the inverse of sine 2t has to have a 2 here and a 2 squared here. So I multiplied everything by a half and introduced the 2 here. So this becomes negative 2e to the negative t. And then the inverse of this becomes sine 2t plus e to the negative t. The inverse of this becomes sine 2t, just like we have seen for this first part. So this first part remains negative 2 plus 1 of the same term gives us a negative of the same term. So 4e to the negative t cos 2t minus e to the negative t sine 2t. Yeah, that marks the end of Laplace transforms. Any questions? Oh, just right on time, 10:57. Any questions? Okay. All the best to everyone, especially in Laplace transforms. And that's it for me. John.
I think we're done for the day. Everyone who was meant to present has presented. So, yeah, I don't know if we're meeting again, because most guys might want to read in the evenings, the day before the exam, instead of meeting. Don't know what you guys think.
Well, I'm thinking we have windows on days like for example Monday night, Tuesday night for this coming week. I wouldn't want to push it to Wednesday night because it's too close. So yeah, that leaves us with Monday night or Tuesday night and then over to the other week, with regard to the weekdays, that is when the exams are actually going on, we have Tuesday night again, because we'll have Wednesday the whole day to like, yeah, but at least coming out from the exam that Tuesday, there is Tuesday night. That is from, I think if I look at my calendar, that puts it right about the 1st of September. I'm talking of Tuesday, the 1st of September, and then back to the week that the exams start. That is Tuesday, the 25th of August, and the 26th, Wednesday of August as well. So, with regard to the weekdays, we could decide what to do with those days, whether to have it or not. But I figured I would bring to attention that those are windows we could use.
Okay, so but now the question stands: will we meet? Do people want to meet? I've seen Daniel asked, what are you going to do about instrumentation?
Sorry?
Instrumentation.
Okay, yeah, we haven't done anything in instrumentation, have we?
Apart from when we had the cut, that was like, I think 1 month ago.
Okay, and instrumentation is on, what is the timetable? Is it on the first week or on the second?
It's on Thursday next week.
Thursday next week.
Yeah.
I guess we could do something with regard to it on Tuesday night, so that we have guys make sense of it on Wednesday.
Fiona is saying he'll set the same question, so
Even better. So I guess we can just go through those questions.
Yeah, Tuesday night sounds great. Like we just Tuesday night.
okay. So we meet on Tuesday next week just for instrumentation.
Yeah.
So same time, same place. Okay, it's Google Meet, so it makes sense. But okay, who will host it?
Do we have to shift? Do we have to shift the? I guess since we are moving closer to having like this kind of sessions wrap up, especially towards with effect to revising towards the exam, I don't think we really should change the links and all, since it's like, I don't know, maybe three more sessions to go.
Okay.
We could keep using your link instead.
Okay, that's fine. So then, today has been a good day. Thanks Celeste, Nigel, Madiba, Peter. Thanks for presenting. So everyone, success on Monday as we do math, and enjoy the rest of your weekend. Bye.
Thanks, Sean.